don't let me forget to hand back the things before you leave today, because sometimes I get excited and forget about those details. So we do have a sheet today. And, So we're going to kind of continue the story problem choo-choo train, because everybody loves story problems, right? And talk about what are called related rates. So essentially, if we think back to when we did implicit differentiation, where we had equations that had multiple variables and we were treating them as all being somehow dependent on, well, like implicit differentiation problem, we had maybe an equation with x and y, and we said, okay, well, x is just a function of x, and so whatever, and y is a function of x, so that we have to do implicit stuff. So with related rates, essentially, it's going to be like that, but everything, all the variables are going to be functions of t instead of x. So if we have something where there's both x and y, the general assumption is that x and y are both going to depend on time. And what that means is that there's going to be dx dt's and dy dt's and things like that all over the place. Okay, so related rates are essentially then just story problems on top of implicit differentiation. Okay, so let's just start with sort of a simple one here. So let's suppose that we've got a rectangle, and let's say it's A units this way and B units this way. Okay, and suppose at a particular point in time, we have A equals 30, B equals 40, and then the next thing is that A is increasing at a rate of 2 units per second, okay? So if I say in English, A is increasing at a rate of 2 units per second, then how am I going to write that mathematically? What is the rate that A is changing? What's the symbol for that? A prime, or another way to write it, dA over dt. Right, okay, so I'm going to write it that way. And let's say it's 2. And then if B is changing at a rate of 3 units per second, sorry, decreasing at a rate of 3 units per second, then what am I going to write here? dB dt is, yeah, -3. Okay, so that's our kind of setup. And so what we want to know is how fast is the area changing when A is 30 and B is 40? Okay, so just some numbers. Now, notice I'm not asking what's the area when A is 30 and B is 40, right? That's easy. We don't need calculus for that. What I want to know is how fast is the area changing, okay? So first off, what is the area of this contraption? Yeah, okay, it's a rectangle, so that's easy. So A is A times B. Okay? And if I plugged 30 and 40 in for A and B, then I would get the area 1,200. Okay, hooray. But I don't care about that. What I care is how fast it's changing. So what do I need to do to find out how fast the area is changing? Yeah, what's its derivative? Okay, so I need to take, all right, so let me just call this the key equation. All right, so like with optimization problems, we had an objective function and maybe some constraints. In with related rates, there's usually going to be a single equation. Sometimes there's more than one, but to start, one that is going to relate all the variables together. Okay, so like an optimization problem, the first thing to do is draw a picture and start to assign letters to things and so on, and then figure out, okay, what's the equation that's going to have something to do with what I care about. In this case, we care about area, so that's our area formula. Okay, great. Now, I need to take the derivative of this. So I need to take the derivative of both sides, but what's the assumption here on little a and little b? They both are variables that independently depend on time, t. Okay, so if I want to take the derivative of AB, what am I going to have to use? The product rule, because neither of them are considered constants. Okay, so if I do that, what's the product rule say? Derivative of product is one thing times the derivative of the other plus the other times the derivative of the one. Okay? All right, so is that okay? We? All right, so, right, just the product rule. And, yeah, I could have written this B prime and A prime and so on, but I think here it's probably good, well, okay, first off, the primes look a whole lot like ones. Okay, so when you're in a hurry, you can slip that up. But what it does sort of do here is it makes clear, and this is the downside to the prime or whatever notation, it makes clear that what is it that A and B depend on? They depend on T, not Q, not X, not whatever thing. We've been explicit as to what they depend on. Now, in physics, I will point out for the peanut gallery, in physics, sometimes what they'll do is they'll put a dot over it. So A with a dot over it, and anytime you see a dot, the assumption is that it's with respect to time. Okay, so that's sort of Newton's notation. And if you put two dots, then it's double derivative, and there's, as you can imagine, if you get to a situation where you need 3 or more dots, you're having a bad day. Okay. Yeah, so that's the physics convention for it, for those of you guys who end up taking some physics. Okay, so what is it that we are trying to find here? We are trying to find the rate at which the area was changing at the instant in time when A is 30 and B is 40. Okay, so we've got here a general equation that relates to all of these rates together, okay, hence the name of the topic, because I've got rates, right, things with d something dt, and they're related by an equation. Okay, do I know what dA dt and dB dt are? Yes, what were they? 2 and minus 3. Do I know what A and B are at the moment in time I'm interested in? Yes, okay. So when A equals 30 and B equals 40, dA dt is 30 times negative 3 plus 40 times 2. Okay, so I'm just substituting in the stuff that we had. Okay, and then we crunch the arithmetic, and so what do we got? We got negative 90 plus 80 is negative 10. Distance units over time units, whatever they are. Okay, does it kind of make sense that, so what does the fact that this is a negative number mean? Huh? Yeah, the area is decreasing, okay, at that moment. Now, is the area always decreasing at negative 10 units per second? Or, hold on. What did I mess up? square units. It's area, not length, right? Did I just blow your mind, Alex? Is it too early for a bazinga? Okay. All right, now let's be clear. Why is it units per, or square units per second and not units per second? I mean, first off, it has to be, right? We're talking about a rate at which an area changes. Well, what is area measured in? Square units. Time is measured in, well, seconds or whatever. Okay, but another way to think about it is, well, if I go back up to my equation here, right? A times dB dt, what's A? It's going to be in units times units per second is square units per second. Same thing for the B dAdt term, and then I add those together, right? So actually, if you think about the units, you can actually use that as a way to catch mistakes, right? Let's say you're working a problem and it's supposed to be a rate of change of area, and you plug it in and you think about the units and you're getting like units per second, but it should be square units per second. That means you messed something up somewhere. Okay, so yeah, anyway. All right, so does it mean that the area is always changing at a rate of -10? Why not? Yeah, okay, it might be the case that area changes at a constant rate, but it's not necessarily the case, right? So here, what is constant as to how fast it's changing? Yeah, the lengths of A and B. Okay, well, just because those things are changing at a constant rate doesn't mean that the area is changing at a constant rate. Okay, so yeah, but yet we got a number here, right? But that number is only valid at the instant in time when A is 30 and B is 40. Okay, if I change the numbers, we'd get different, potentially, answers. Okay, now, the other kind of rule of thumb that I would use for this is, what would have happened if I plugged 30 and 40 in to my area formula from the get-go? I've gotten area equals 1,200. Okay, great. And then I said, well, I want to know the rates of things, so I'll take the derivative of that. Well, what's the problem? You'd get 0, right? The derivative of a constant is 0. So one of the mistakes that you can make on these sorts of things is to plug in numbers too soon, because if you do that, you will miss the calculus part. Okay, so hold off on plugging in numbers until after you've taken derivatives, not before. And that will, by and large, save you from that headache. Okay, now, there's maybe a few exceptions to that rule, but by and large, that I've found that will save you trouble. Okay. Okay. So does this kind of make sense what we did, right? We started by drawing a little picture, and I know for a rectangle, it's not exactly all that important. The key equation is the key to this, right? What relates the variables that you care about together so that you can then take a derivative and go from there. Okay? All right, so that was Buffalo mild. Let's go up to some, some hot barbecue or honey barbecue. All right, so spherical snowball melts. There's my fancy spherical snowball, okay? And it melts in such a way that when the radius is 20 centimeters, its radius is decreasing at 3 centimeters per minute. What rate is the volume of the ball changing at this instant? Okay, so I've got my cheesy snowball there. I should call the radius something. Well, how about r? Okay. And what do we care about? So what are we given? What's the rate at which r is changing? Yeah. Okay. And so dr dt is 3 centimeters per minute? Huh? Thank you. Minus 3. Okay, because it's melting, right? Okay, and we're interested in the moment in time when the radius is 20 centimeters. Okay, that's a big honkin' snowball, by the way, right? Because that means it's over a foot in diameter, right? You know, this is like what the teaks do whenever it snows and they build a wall out in the mall, right? And make Beta pay for it. See what I did there? Yeah, okay. All right, so what's the key equation here? Or, well, first off, have we missed any variables or any other things of interest for now? The volume, okay, so what's the volume formula? That's what we need, right? Almost. 4/3 pi r cubed. And we all remember those formulas, right? Yeah. All right. Now, in this particular case, we only have really two variables. V, the volume, and R, the radius. Do I have to do the product rule with the formula 4/3 pi r cubed? I could, but I don't have to. Why? Because, well, 4/3 is a constant, but also pi is a constant, right? If I did do the product rule, then I would get to a point where I'd have to take the derivatives of 4/3 pi, and what is the derivative of 4/3 pi? So no worries, right? So think for like 2 nanoseconds before you plunge into taking the derivative, whether or not you really need a rule. Okay, so dv dt is 4 pi r squared times dr dt. All right, now let's pause for a minute and make sure that I'm not full of crap there. Why is it that? Okay, so what's the derivative of r cubed is essentially the question. Well, do we all buy the 3r squared part? Okay. And where did the 3 go, by the way, while I'm at it? Right. Cancels with the 3 that was in our 4/3. Okay, so I can get rid of that. But, so we've got the r squared. Why do I have to have the dr dt tacked on there? What forced that? Yeah, okay, that's true, but go deeper. That's not quite. R depends on t, and the chain rule says we have to do that, right? Because what did we just take the derivative of? R cubed. So what's the derivative of something cubed? 3 something squared times derivative of the something by the chain rule. Okay, so, all right, so we cool with that, right? That's the, if you forget those things, by the way, if we forgot dr dt here, you'd be kind of stuck, because where would we plug in the fact that we know that dr dt is, what, -3? We wouldn't have a spot to put it. Okay, so like with implicit differentiation, you have to really be careful and respect the chain rule on these guys. And if you don't, woe unto thee. Okay, good? All right, are we cool with the key equation? dv dt is 4 pi r squared dr dt. Oui? No. Okay, so what's the instant in time we care about? What was the radius? 20 centimeters, and the rate was this. So the rate of the volume is 4 pi times 20 squared times minus 3. And let's see, what do we get? 400 times negative 12 times pi. Okay, whatever that number is. I don't really care. Okay, does it seem reasonable though? I mean, numerically, what was that roughly? When you throw in the, did you calculate it? What'd you get? All right, 15,079, whatever. That's pretty fast in some sense. Okay, but also we got a pretty fat, or we have a pretty thick, with 2 C's, okay, snowball here. So I guess that's reasonable. Okay, good. All right, so what was the step here? Or what were the sequence of steps, right? Draw a picture. Label things. In this case, there was only one thing to label, the radius. What's your key equation? Okay. Then take the derivative and start plugging stuff in. Okay, now, of course, we're going to make them more spicy, right? We may not get all the way up to Blaze and Challenge this today, but guess what we're doing on Wednesday? Huh? No. Well, we'll get to mango habanero. Okay, so a guy's going to fly a kite 150 meters high, and the wind is going to move it horizontally away from him at some rate. In order to maintain the kite at a height of 150 meters, he's got to let out more string. Okay, makes sense, right? If it's straight up from him and it's, 150 meters up, then there's only 150 meters of string. But if it blows horizontally and he doesn't let out any string, what's going to happen? It's going to lower in its altitude. But if he lets out more string, it'll stay at 150 meters altitude, but just get further away from him. Okay? All right, so that's sort of the story here. And what we want to know is how fast is the string going out when he's let out exactly 250 meters worth of string? Okay, so does that, the story make sense? Huh? It's a lot of string, but whatever. Huh? What do you mean? It's like 2 in 1. 2 in 1? It's 2 races in 1. Yeah, well, that's what makes these fun. Just wait until Wednesday. Wednesday, I'm going to give you a very famous problem. Well, it's not particularly famous, but I remember it from high school. It was, we called it the coffee pot problem. So there was a coffee pot, and you had to, water was flowing into the top part, filtering through the coffee filter, and then into the basin below, and you had to figure out all the stuff. It was a fun one. So Miss White, if you're out there listening, that was my calculus teacher in high school. Okay, so first step, are we kind of clear what the story is? Okay, so let's draw the picture to go with the story. All right, so the dude's here, and the kite is up there. Well, okay, I can do a little bit better than that. Is that kite-like enough? Is that good enough? Yeah. So, actually, let me go on a little tangent for a moment. If there was one thing I could do in my career differently, like go back and tell 15 years ago me to do something, it would be every time I get a goofy drawing on an exam or quiz or something, to make a copy of it and save those, because after 15, 20 years worth of teaching, I'd have enough to publish a book of stuff students draw on exams. And believe me, I've gotten some really funny ones. I've got some that aren't fit to print, but, you know, calculus tends to bring out the worst in people. So, all right, so what's changing here? I've got the length of the rope, or the string, so let me call that L. All right, and I've also got here the distance that the thing is away from my guy, x. Okay, what should I call the third leg of this triangle? All right, we got two options. We could call it y, but in this particular case, what's the assumption? Yeah, that one thing is constant. Okay, he's letting out rope exactly so that the altitude of the kite stays the same. Okay, and the altitude of the kite in this case is 150. Okay, now the other starting assumption, I guess, is that the way I drew the picture is as if he's laying on the ground, but does that really matter? No. Okay, so got that, and now what are we given about dx dt and dl dt? Well, how fast is x changing? Yeah, 5 meters per second, and that was constant basically because the wind. Okay, how fast is L changing? Right. Okay, that's the thing we're trying to solve for. Okay, so maybe it's good to notate, hey, that's what we want to solve for, so it's okay we don't know it yet. All right, so what's the other thing that we're missing? We need a key equation. So what equation relates all these variables? Yeah, okay, so what's Pythagoras' theorem say in this case? X squared plus 150 squared equals L squared. Okay? All right, now, you might say, wait a minute, Dr. C, we're trying to solve for the rate of L. So why don't we solve for L in my key equation and then take the derivative? That would be okay. What's the advantage of leaving it like this? Well, we will have to do the chain rule, but we don't have to do lots of chain rule. In particular, what does not solving for L save me from? Saves me from a big, nasty square root, okay, which would mean that the derivative of the left-hand side would get more complicated. Okay, we could do that. Like, it would be okay if you did. Okay, but if we don't have to, then let's avoid it. Right, so this is the moment as being a mathematician. I had another teacher in high school, college, named Dr. Q, we called him, Dr. Quintanilla. And he always would say, mathematicians by nature are lazy creatures, and so, you know, be lazy. All right, so what's the derivative? What's the derivative of x squared? Two x I need to turn up my battery here. Huh? No? No? Well, okay, yes, but symbolically, what did you just do? Right? What's the derivative of something squared? 2 times the something to the first times the derivative of the something by the chain rule. Okay, so dx dt. All right. What about the derivative of 150 squared? That's where the 0 comes from. Okay, because 150 squared is a constant. Okay, and interestingly enough, right, this is sort of the fun thing about doing related rates, is that did the actual number 150 matter? Nah, not really, or at least not yet. Okay. All right, equals what? What's the derivative of L squared? 2L L prime. Okay. All right, good. All right, so key equation, then we took the derivative and obeyed the chain rule the whole way. Okay, once we've got it differentiated, which we do now we can start plugging stuff in. All right, so do we know what L is? Reread the problem. Yeah, we're interested in the point of time when L is 250. Okay, so great, we know L. Do we know dL dt? No, but that's what we're solving for, so that's okay. Do we know dx dt? It's 5. Okay, great. Do we know x? We don't, do we? But we could solve it, exactly. Okay, so we do not know at the moment in time where we have 250 on the hypotenuse, 150 for the height, x here is, we don't know the number, but could we solve for it? Yeah, okay. How do we solve for it? Well, guess what we get to use again? We've got a relationship between them, right? Okay, so let's come over here and do that. If x, or sorry, not x, L equals 250, then x is the square root of 250 squared minus 150 squared. Okay, which is going to be, well, let's think of it this way. It's time for the wizarding world of oh, that's nice. Yeah. Okay. All right, so all that fancy schmancy factoring foo, which maybe it's way too early for that, for you guys. And I haven't even had my coffee yet this morning.
Do you have something against calculators?
Huh?
Do you have something against calculators?
Huh? Yeah. They're idiot boxes. Yeah, exactly. It's like Klingons and Tribbles, right? They're sworn enemies. Math teacher. No, I don't really have that much against calculators, except when students either use them when they're completely unnecessary or use them when they're completely inappropriate. So, yeah, like, you know, if somebody needs to bust out a calculator to multiply something by 10, we have a problem. Speaking of which, did I ever tell you a story of when I was in college? and the 90% off at the store. Have I told you guys this one? Okay, so in college, amongst other jobs, I worked at Kohl's, the department store. How many of you guys have been to a Kohl's? Yeah? How many of you guys have a Kohl's charge? Or your parents do? Oh, you don't have a Kohl's charge. Well, I can sign you up for one today. We can apply, and I'll save you 30% off your purchase. All right? You falling for that? The interest rate on those cards, by the way, is obscene. It's like 20-something% APR. So, yeah. The store always wins, right? In fact, it's kind of sad. Kohl's makes just as much money off the interest on their cards as they do the entire operations of the store, right? Like, it's that valuable. So you think you're getting a great deal, but somebody's getting screwed. This is credit 101. Pay the bill on time. Okay, anyway. So it's a day or two after Christmas, right? What happens after Christmas every year at any store? All the Christmas stuff gets super marked down because we need it the heck out of the store because we got to start setting up for Valentine's Day or whatever the next thing is. Okay, so and the discounts get progressively better because we're more and more desperate to get rid of stuff. So a couple days after Christmas, a lady comes up to me with an item, and she says, "So all the Christmas stuff is 90% off, right?" "Yes, ma'am." "Can you tell me how much this is?" She hands me an item. Okay, now to be fair, that's a good question because the game, you have to know this, right? When they say 90% off, what do they mean 90% of? The original price, which is what's on the sticker or the barcode, right? Not the sale price, the original price, okay? So flip over the item, find the barcode with the sticker, and it says it's $30, so, all right, here you go, ma'am, it's $3. She's like, "Oh, wonderful." So about 10, 15 minutes later, she finds me, and she's got like a cart full of stuff. She's like, "Can you tell me how much all of this stuff is?" I'm like, "Yes, ma'am." $250, $3, I'm just blasting through these. She's like, "How are you doing that so fast?" I'm like, "Well, 90% off means 10% of. And fortunately, we use a base 10 number system, so I just move the decimal point one spot to the left, and here you go." She's like, "Wow, you must be really good at math." I'm like, "Well, I am a math major, but yeah, that was a sad day." All right, so anyway, we got 200. Now, I suppose I should have realized that because this is in disguise a 3, 4, 5 right triangle. But, yeah, anyway. All right, so 200, great. Now do we have all the pieces we need to plug in? Yeah, okay. We know x, we just solved for it, it was 200. We know dx dt was 5. We knew that L was 250, that was given. And dl dt was the thing we were trying to solve for. Okay, so if you hit this point, like let's say we had just plugged in everything we knew in the beginning right away, we would have still had a second variable there, namely x. Okay, so that's what told us we had to go solve for it, because you can't solve an equation that has more than one variable in it and get a number, right? You have to have a single variable. Okay, so got dl dt. Is that the only variable in my equation? Yeah. All right, and so now what? Can I solve for dl dt? How, pray tell? Well, or divide, but same difference, right? All right. So what's 200 over 250? 4/5 times 5 is Did I get the arithmetic right? All right, and what are the units, by the way? Right. Okay. So that's the rate the rope is going at. Okay, so let's kind of recap what was the procedure. Draw the picture, label stuff, figure out your key equation, take the derivative of the key equation, and that's the point where we realize, wait a minute, I need to know x. We knew everything but dLdt, but we also didn't know x, so we better find a value for it. And that's when we did the stuff over there on the right, okay, so that we could then finish it off. All right, so kind of makes sense? All right, so this one was a little nasty, but more from the arithmetic department than anything. Yeah, okay. So let's get one more going off. All right, this one's a little funny. So there's a rock on the shore. And 100 yards east of the rock is a lighthouse. And 173 yards north of the rock is a motel. Okay, do you guys like how the spelling is there? Yeah, we were real clever when we wrote this problem. Okay, and so what's happening here? What do lighthouses do, right? They got a beam of light, and that beam of light rotates. Okay? And in this case, we're told it rotates twice a minute. At the moment that the beam hits the motel, how fast is the beam moving along the coast? All right, so first off, let's draw the picture. The rock is here. 100 meters this way is the lighthouse. 173 meters north of the rock is the hotel. Okay, good. All right, so that part's okay. So the beam of light's going to rotate. Okay? And we want to know how fast is it moving along the coast when the beam is pointing directly at the hotel. Okay, now there's actually two ways to think about this, because what about the beam has not been stated? Okay, how fast does it rotate? That was given. Twice a minute. Okay, what was not given about that, though? Which direction it rotates. Is this thing going clockwise or counterclockwise? Well, basically, if we pick one versus the other, it's going to be the difference of a negative in our answer, because if it rotates one way, it'll be moving up the coast. If it rotates the other way, it'll be moving down the coast. So the rates will be the same. It'll just be a plus versus a minus. All right, which way do you guys want the thing to rotate? Clockwise? Clockwise? All right, fine. So if the beam rotates this way, okay, then at some point it's going to be like this. Okay, and let me call this unit X and this unit L. Okay, and then also there's an angle there. Okay? So, and I need to have the angle because we need to translate how fast this thing is rotating into something involving our triangle. Okay? All right. So in this case, what do we care about? What are we trying to find? We're trying to find dx dt. Right? How fast is the point of the beam of light where it intersects the shoreline, how fast is that thing moving? Okay. All right. What were we given about the rate at which this thing is rotating? Twice a minute. Okay. So if it's rotating at twice a minute, then what is, sorry, not theta, what is d theta dt? Okay, so, well, first off, we need to choose our units, okay? And actually, this is really important. What's the derivative of sine? Sine of x, say. Cosine of x. I maybe mentioned this when we did that, but that assumes that x is measured in radians. If you do it in degrees, then the derivative is cosine x times this like horrible pi over 180 thing, right? Okay, so we have to measure in radians to use calculus formulas. So why don't we use radians here instead of degrees? Okay, that'll save us some trouble later. Okay, so if it's 100, if it rotates twice per minute, that's 360 degrees per, well, it's actually 720 degrees per minute, right? What is that in radians? Well, what's 360 in radians?
2 pi.
2 pi, so what is it in? Twice per minute would be 4 pi. Okay, so 4 pi radians per minute. Okay, and I'm going to kind of be explicit here that we are using radians just to, for the next step. Okay, now, what we care about is something involving x. Do I actually care about L, which would be the distance from the beam of light to where it hits the shore? In this particular problem, I don't care about it, so I labeled it for no reason. What I care about is x. So I need a formula that relates x, 100, and theta. Tangent, okay, is the one that I want. All right, so what is tangent of theta? X over 100, right. Okay, opposite over adjacent. Okay, good. All right, now, so that's our key equation here. Okay? All right, now we want to differentiate. So what's the derivative of tangent? Secant squared okay, secant squared theta times d theta dt. Okay, why is the d theta dt there? Because of the chain rule. Right? And then on the other side, I just, for cleanliness, wrote it 1 over 100 times dx dt. Is that okay? Okay, so what are we trying to solve for here? Yeah, we're trying to solve for dx dt. Okay, so so all I have to do is multiply by 100 to get dx dt by itself. Well, let me put the 100 out front. Okay. Now, do we know d theta dt? Yeah, that was given, what do we have, 4 pi or whatever it was? Do we know secant squared of theta? No, because we don't know theta either. Okay? So we need to solve for that. All right, so let's go over to the right. Now, what is the particular value of theta that we're interested in? We're interested in the moment that the configuration is thus. Okay, because we're interested in when? The moment that the beam hits the lighthouse, or sorry, the hotel. Okay, so can we solve that triangle? What do we know that tangent of theta is in that triangle? So in this triangle, what's tangent of theta? Over 100. Okay, now, here's where if you pull out the calculator, you'd say, oh, well then I can just arctangent it, get the angle, take the secant of that, and then square it. And that'd work. Do we need to do that, though? What do we care about? We care about secant squared of that theta. What is secant in terms of the triangle? Huh? 1 over cosine, or hypotenuse over adjacent, right? Could I solve for the hypotenuse using Pythagorean theorem, and then, once I've got it, do 100 over that thing, or sorry, that thing over 100 would give me the, yeah. Okay, so we're out of time, so why don't you guys do this? Finish this one off for next time, and we'll double check it right at the beginning. And then on Wednesday, my plan is basically we're just going to do more of these problems. Okay, kind of pull off the training wheels a little bit. Sound good? Oh, there's good news. I have very good news for everybody. So it's like in Futurama. Great news, everybody. What are we going to do on Thursday? What am I going to give you guys? It's not just a bonus reassessment, but it's a bonus reassessment of Palooza. Right? Okay, so there are 2 times you can do it, at 11 or at 4-ish. I will need to double check on the location. Okay, so I'll post the details to Canvas, but I'm going to give you guys a surprise bonus reassessment. Any complaints? Oh, sorry, Ian. And grab it. No? It'll be fun. All right, see you guys later.